Hello CIO world, and welcome to another study theme of chemical engineering design. This is Conduction Revisited. In the study theme, we will go over the multidimensionality and time dependence of heat transfer and take another look at 1D steady state conduction. We will of course make use of boundary and initial conditions that are required for solving various problems of heat transfer, and also take a look at temperature distributions, 1D heat conduction that involves heat generation, and also evaluate the extent of heat conduction, looking at temperatures, etc. You should be familiar with the three main types of geometries that we've dealt with before, and namely these are involving rectangular, cylindrical, and spherical coordinate systems. Recall the applicable coordinates that are associated with each of these systems, and remember that heat transfer may also depend on time. Although most of our applications tend to aim for some sort of steady state operation. The following equations are applicable to heat being transferred through these geometries respectively. And what I'm showing here is the typical dt, dx, dt, dr that we have dealt with before. Note that these are simplifications, and we will need to use the general heat transfer equation to derive these equations in the first place. Right, let's take a closer look at heat transfer through a rectangular geometry. As shown here, heat is transferred from the left side of the object, and this heat is then conducted through from left to right. The properties of the object in terms of its ability to conduct heat through itself is given by K, which is the thermal conductivity for the material, while the driving force for heat conduction would be delta T, which is the temperature gradient. The result is heat being conducted through an area that is exposed to the heat source, which is Q dot. The initial conditions are considered at time t0 at positions x equal to x1 and x equal to x2 as shown, where t is equal to t1 and t is equal to t2 respectively. If steady state flow in energy through the system has not yet been achieved, then these initial conditions specified may still change. So at time t equal to t1, t2, for instance, may have increased. All right. And we may still increase up to some time of t3, for example. It may also be the case that once steady state conditions have been achieved, that reduction in the temperature gradient may result as shown, and also T1 could have also shifted in the process. However, the thermal conductivity may have also changed slightly too, and these also need to be considered together. So it is therefore necessary to consider all initial as well as final conditions for a particular problem that is analyzed. Okay, and you need to make sure that initial conditions are not changing, or they are changing, and then make a decision based on that. So let's continue on refreshing our minds by considering the following elements again. So heat transfer takes the form of heat that is flowing as energy, okay, and it proceeds from T1 to T2 through this rectangular element. Now, when we are at steady state, or steady state has been reached, we know that Q dot in is equal to Q dot out, and that this is equal to Fourier's rate equation for heat conduction, which is Q equal to minus K times by A times by nabla T. This is a simplified form of our heat transfer equation. So in our analysis, we decide, for example, through which area heat is being transferred, or through which area heat is flowing. The area is always perpendicular to heat flow. So the area that we consider must be perpendicular to the heat flow. Always remember this. So therefore, the area profiles we need to consider in this case are shown by the varying colored squares going from orange to yellow to green. So in other words, the area in question here is y multiplied by z. It is important to consider the temperature gradients as well, and also make sure that where temperature gradients do exist, okay, so let's have a look here, dt, dy, dt, that should be td, dz, the one in the z direction. So we consider all of this, and in this case of heat transfer as shown here, we know that the temperature gradients in the y and z directions are 0, and so our nublet T simply becomes dt dx. Okay, the equation that we have been using is a simplified form, the Fourier rate equation, and it's simplified from the general form of the energy equation as is seen here. So the first three terms of this equation correlate to heat conduction, which we have been looking at up to now. So notice the presence of the thermal conductivity terms as well in each of these terms. This implies that the thermal conductivity can also vary with dx, dy, ddz, etc. Now, thermal conductivity may be a function of position. So, at time x, it could be one value at time y, at position y, it could be another value, etc. So, since each position would have a different temperature, of course, there exists a temperature gradient from, going from one position of x to another position of x, etc. And more often than not, thermal conductivity is taken to be treated as a constant. So if we treat it as such, we can remove it from its brackets as shown here below. Now, if heat transfer has reached some steady state value, we do not need to then consider the right-hand term, which takes into account any variations of time. Okay, so dt, dt. How does temperature change with the change in time? Sometimes also we would not consider heat being generated within our system. It depends on how we've drawn our control volumes, of course, as you remember from COP. And therefore the following term can also be cancelled out. And we could also have both instances where heat being generated and any variations in time are negligible, okay, or just don't apply. So another type of geometry that we could be working with in COP a lot is the cylindrical geometry, since a lot of the equipment used for heat transfer, for instance, make use of pipes. We also consider these 1D applications applicable, where heat transfer can either be in the z direction or in the radial direction, as I have shown here. Now let us consider a few examples. In this example here, we are told that we have an aluminium pot, aluminum if you're American, and the aluminium pot is being heated on an electric stove. We are given the dimension of the base of the pot, and we are also told the wattage of heat, and we are also given the efficiency of heat transfer from the source to the pot itself. We're also given the base, the bottom surface of the pot area, and we're also told that it's operating in steady-state conditions, and we are being asked to find an expression of the boundary conditions at the bottom of the pot. So firstly, we can assume 1D heat transfer. This is through the z direction. So using cylindrical coordinates as our coordinate system, we can simplify our general heat equation under consideration and say, well, that heat is only being transferred in the z direction and there's no heat being generated within the control volume that we're looking at. Right, we can obviously integrate this equation, and if we do that, we obtain Fourier's rate equation for heat transfer being conducted. Next, we need to consider the heat that's actually being transferred to the pot, so we have to take into account both the efficiency as well as the surface area. We know that the heat, the wattage being generated or being provided is 800 watt. Okay. We also know that this is 90% efficient, and so transfer effectively is reduced, and that heat is being transferred through an area that is equivalent to the 0.2 meter diameter base. Okay, given. We equate the resulting heat flux that we've calculated to the equation as shown. And lastly, we can determine the boundary conditions applicable. So we already know at L equal to 0.03 meter that the temperature is given to us as T2 equal to 110 degrees Celsius. If we know the thermal conductivity for aluminium, which we can obtain from literature, so in other words the textbooks for this module, we will be able to specify the other boundary condition. Now before we continue, let's just briefly discuss the spherical geometry, which will also sometimes be given in problem statements, especially in the tutorial questions that are to follow. Sometimes we need to consider, for example, heat being generated in a spherical ball of matter, and therefore the following equation would apply. Other examples, okay, I show cylindrical coordinate system here, but or spherical coordinate system, but this could have been a cylindrical coordinate system. But geometries that pertain to spherical coordinate systems could be things like nuclear reactors, which use a pebble bed. We could have chemical reactions which use spheres, but we may also have to consider heat generation through a cylindrical electrical wire, or even mechanical energy due to friction over a wire. Okay, so let's consider our next example. Alright, so we are told that a wire generates heat through electrical resistance, and we need to quantify this in two ways. We are told that the wire is 80 centimeter long and it is 0.3 centimeter thick according to the diameter, and that this wire discharges 1.2 kilowatt of energy. Okay, we define the heat being generated by the following equation, and this is per volume. Now, yeah, we may already know what the heat being generated is. In this case, we are told that it is 1.2 kilowatt of energy being generated. And next, we determine the volume of the heating element through which this heat will be dissipated, that's being generated, and it's given by the length of the wire multiplied by the cross-sectional area of the wire. And so the volume can be calculated thus. And by dividing the heat generation by the volume of 5.655 centimeter cubed, which we've calculated, we obtain a volumetric heat generation value of 212 watt per meter cubed. Next, we need to determine the heat flux through the wire, and again, we consider the heat being generated as 1.2 kilowatt of energy. The area through which the heat generated is being discharged is given by the surface area, which is equal to the circumference multiplied by the length. And this is pi dl, where pi is simply the circumference divided by the diameter. Right. We also know that the area, as we've calculated it to be is 75.4 centimeters squared, and we can therefore calculate the heat flux, which is 15.9 watt per centimeter squared. Right, let us quickly consider some boundary conditions and initial conditions. How will we generally read this from our problem statements? Well, first off, we may be provided some constant temperature at a time of t equal to t0, or we could also be given a relationship for temperature T as a function of its position. Okay, boundary conditions can similarly be in the form of a constant temperature, or we can also be given a temperature as a function of position, or we could also be provided information about thermal conductivity as a function of temperature. Okay, so before we go on to the last exercise for this lecture, let's consider some useful tips, and it goes without saying that firstly, be sure to read the problem statements very carefully. Sometimes you will have too many considerations in your mind, but try not to overcomplicate the problem. Just keep it simple and only read what is written, and do not read too much into the problem statement either. Sometimes we will end up overcomplicating the problem when it's actually just very simple. So don't try to read too much into a problem. Just consider what is being said in the problem and keep it simple. Also make sure to identify any boundary conditions and decide what heat transfer mechanisms are applicable. Lastly, set up your equations and solve the problem. So let us turn to our textbook and look at a more in-depth problem. This is problem 2-12, and this is on page 96 of the 5th edition of our textbook. Right, so once you've read the problem statement very clearly, go over it again and identify all the useful bits of information that are present. So also take note that there may be more than one question that is being asked. And look out also for simplifications that are already given to you. For example, disregard heat loss by radiation. Right. It is always necessary to consider all aspects of the problem, which can be summarized as follows. So these take forms of assumptions or just simplifications. So we can take heat transfer, for example, to be steady and in only one direction. We can treat the thermal conductivity and the convective heat transfer coefficients as constant. Since we will only consider boundary conditions next to the heating element, we do not need to derive our heat transfer equations to include generation of heat. This is a very useful simplification to be considered. Also, we are told that radiation is to be neglected, as stated in the problem statement, although this may not actually be a very good assumption to be making. So just be careful. Sometimes you'll see in the textbook that it does this, but personally I would not have neglected radiation because we work with very high temperatures, and we also end up with very high temperatures to begin with, which are not maybe applicable to this problem. Okay, we're also told to treat insulation as being ideal. Okay, so heat transfers only in one direction, from left to right in this case. So for this problem, we consider determining the heat flux first, which is quite easy, straightforward. It's calculated as 40 kilowatt per meter squared. Okay. Next, we consider our first boundary condition that involves heat being conducted through the base, and equate this to the heat flux, which we have just calculated. Now this helps us to define our first boundary condition, okay, as shown. Now the second boundary condition at position x equal to L, we consider that heat through the ion base must equal the heat being dissipated into the surrounding air. So in other words, we can equate conduction to convection, which is pretty obvious, right? We therefore obtain the second boundary condition as shown at position x equal to 0.005 meter. Let us consider answering the very first question that we have been asked to solve, and this is namely to obtain an expression for the variation of temperature in the base plate. What this is asking is for an expression of T, temperature, equal to something else based on boundary conditions. Okay, so we're not sure what C1 or C2 may be. Let's take a look at our general heat equation and simplify it for this particular problem. We end up with something that looks like the derivative of Fourier's rate equation if we simplify all the little bits and pieces of the equation. So the first integral obtained from integrating this equation with respect to dx, we know to be a constant, C1. So the question is, what is C1? C1 is the steady state heat transfer, Q dot, divided by the thermal conductivity, which we have also taken to be a constant. On integrating again, we obtain the equation we had been required to find, but actually we still need to define the constant C2. So we need to find C2, and we do this by using or applying the second boundary condition as follows. At x equal to L, we know that the conduction equals convection. Okay, so here we already know an expression for temperature T as a function of L, and we also know what dt dx is equal to. We've already found this before and equated it to C1. So we substitute into our expression for C1 equal Q dot over K, and also temperature as a function of L, which is equal to Q dot multiplied by L over K plus C2. And next we can then solve for C2 to obtain C2 equal, C2 is just equal to temperature of the surroundings plus Q over H and Q multiplied by L over K. Okay, so we therefore have sort of answered the first part of the question. Okay, so we've done this by substituting in C1 for the thermal conductivity ratio and heat transfer ratio, etc. Okay, so the expression that we get to is T as a function of x. Okay, so x can go from 0 to L is equal to the following terms, which are for the thermal conductivity as well as the thermal heat dissipation via convection. Okay, so the convective heat transfer. Right, the second equation that we are asked, the second part of the problem we are asked to solve is to determine the temperatures at the outer and inner surfaces. Sorry, there are cats that are busy distracting me at the moment, so I need to pay more attention to not looking after cats. Okay, now to determine these two temperatures, we do this by just applying the boundary conditions. The first boundary condition that we have is x equal to 0 meter, and the temperature that we calculate in this case is T equal to 533 degrees Celsius, which is pretty high. Okay, now let's look at the other boundary where x is equal to 0.005 meter. We find a temperature of T equal to 520 degrees Celsius. So just to be clear, again, I would not have made the assumption that radiation is negligible based on these temperatures that have been obtained. Just to give you an idea, a hot fire, a wood fire, is at a temperature of 650 degrees Celsius. And if you've ever sat next to a fire before, you would have felt the radiation on your face, right? So this tells me that these temperatures are really high for the iron, and I would have considered radiation. So see if you can determine what these temperatures would have been if radiation was accounted for in this case. Okay, next we can actually do this problem in a less complicated way, but in my opinion this is also a less beautiful way. But nonetheless, you would have probably followed this derivation instead. So firstly, we equate conduction to convection. Okay, this is the obvious assumption that we've applied, steady state conditions. So Q via conduction must be equal to Q via convection. Now between the two boundary conditions, we have conduction, and the expression for this is shown here. We see that we also have two unknowns, T0 and TB, and therefore we require a second equation. Two unknowns, we need two equations. Before we do this, let's just quickly rewrite the equation as follows, and next we can consider the equation for convection. Since we have an expression for TB already, as shown here, we can substitute in this expression for TB. Okay, so we end up with the following equation, and on simplification we obtain the following, which can then be rewritten as follows. And realize that this expression is the same expression as we obtained previously using the other method of derivation. So therefore there may be many ways to obtain the same result or skin a cat, which I would really like to do right now. These cats are really bothering me. So this concludes our discussion on conduction revisited. Cheerio!